Another way to simplify complex circuits is by using Kirchhoff laws. In this video, we'll try to understand and apply Kirchhoff's rules. Complex circuits may contain multiple components such as resistors and voltage sources. Don't be confused when people say Kirchhoff's rules or Kirchhoff's laws because they pertain to the same thing. The junction rule is the same as the Kirchhoff's current law, while the loop rule is the same as Kirchhoff's voltage law. Okay, applying Kirchhoff's rules in a simple problem will help you understand the process. Let's determine the current through, voltage across, and the power dissipated by the resistors in the given circuit. Most of the time, these are the types of questions when you are dealing with Kirchhoff's rules. Before anything else, analyzing the circuit will be the key in applying the rules. First, label the components such as the resistors and the voltage sources. So here we have R1, R2, R3. We can name voltage sources as a VA and VB. I don't want to name it V1 and V2 because you might think that V1 is the voltage across R1, which is incorrect. Next thing is to trace the path of the current. If I'll start from the positive side of VA, so this would be I1, which will run through resistor 1 until encountering the first junction. This is the important one. At this junction, I1 splits to 2. We can name I2 and I3. I3 will run this side until facing another junction, where it will meet with I2 to form I1 again. Well, this is if I am right because what I did here is arbitrary, or I just choose it that way because there are other ways that the current might run in this circuit. Like for example, from this voltage source. So this would be I1, I2, and I3. Anyways, the important thing here are the currents at the junctions because those are where the Kirchhoff's junction rule will apply. Basically, the currents through the resistors that the problem is asking are I1, I2, and then I3. The rule of the thumb here is that if you have 3 unknowns, then you need 3 equations. The first equation will come from the junction rule or Kirchhoff's current law or KCL. Accordingly, the sum of all currents entering a junction must equal the sum of all the currents leaving the junction. If we consider this junction, I2 and I3 basically splits from I1. Or you can say I1 enters the junction while I2 and I3 are leaving the junction. Effectively, we can say I1 is equal to I2 plus I3 following junction rule or the law of the conservation of charges. If you are wondering, the same thing is in the other junction. I3 plus I2 is equal to I1 because I2 and I3 are entering the junction and I1 is leaving the junction. I will only use the first one and will be our first equation. Now, the other 2 equations will come from the loop rule or Kirchhoff's voltage law or KVL. The law states that the algebraic sum of changes in potential around any closed circuit path must be 0. This is the equivalent of the law of conservation of energy. The changes in potential here is actually the voltage, otherwise termed as electric potential difference. To apply the rule, let's look at the first closed circuit here. You notice there are 3 components. We have voltage source, R1, and R2. In simple words, loop rule is telling us that the voltages across each component should be equal to 0. But not that simple though. We need to follow some steps. First is to draw a loop that will cover the entire closed circuit. The direction is arbitrary, so you can choose clockwise or counterclockwise. I'll be doing it in clockwise. Okay, so let's start adding the voltages of each component. Let's begin with the voltage source here. That is 10 volts. The rule here is like this. If your loop will run to the negative side of the voltage source first before the positive side, then the voltage is positive. If positive to negative, then the voltage is negative. Since our loop passes negative to positive, so we have positive 10 volts. And so, we add this by the voltage across the second component, which is a resistor. How do we get the change in potential here? Yes, you're correct. V is equal to the I times R. The current here is I1 and the R is 4 ohms. To identify if we have negative voltage here or a positive, we follow this, SIN. If the current is the same direction with the loop, then we have a negative potential. So if you follow our loop, it will have the same direction with I1. Therefore, we need to include minus a sign here. Next component is R2. So that is I2 times 2 ohms using V is equal to IR. You would notice that I2 will have the same direction with our loop. That's why we need a negative sign here as well. All of this is equal to 0, giving us our second equation. That's what we get from loop number 1. And for the third equation, we look at the second loop. The components here are R3, voltage B, and again, resistor number 2. Randomly, you can choose the direction of your loop. It does not need to be the same with the first loop. I will be choosing clockwise here again. So I will start with voltage B. Since the direction of my loop will pass from positive to negative, then I will write negative 20 volts here. I add that with the voltage across R3. Using V is equal to IR, we have I3 times 3 ohms. I3 is the same direction with the loop, so that would be negative. And lastly, at resistor number 2, that would be I2 times 2 ohms. This time it would be positive since the direction of I2 is opposite the direction of the loop. This is also equal to 0. Now we have our 3 equations. We can actually clear everything because what we need right now is our algebra skills to combine all these equations for us to solve for the currents. Before that, I have here some tips when solving for the currents. You can drop or discard the units while solving for the current, but make sure to write them later on. Rounding off, if possible, should be done at the end. Let me simplify the 3 equations first. Equation number 1 is I1 is equal to I2 plus I3. Equation number 2, we have 10 minus 4 times I1 minus 2 times I2 is equal to 0. Equation number 3 is negative 20 minus 3I3 plus 2I2. Same, equal to 0. Let's try to combine equation 1 with equation number 2. Let's try to write equation number 2, but instead of writing I1, we substitute it with I2 plus I3. After that, we can simplify it by combining like terms. We can simplify this further by obtaining the value of I2 in terms of I3, and let's call this new equation as equation number 4. Now let's combine equation number 4 with equation number 3. Let's write equation number 3 here, but instead of writing I2, we will insert the value of I2 in terms of I3 from equation number 4. And there you go, we were able to eliminate I2 and then I1, so we can solve for I3. But again, there are many ways on how you can solve this one. This is just my way. And to simplify this further, as usual, we combine all the like terms. And finally, we have the value of I3 here. I3 is equal to negative 3.85 amperes. Now let's talk about the negative sign here. The negative sign here means that the direction that I have chosen in the circuit is actually the opposite. But the magnitude here is correct, and that's the important thing. Now using the value of I3, we can solve for I2 using equation number 4. That will give us 4.23 amperes. And our direction is actually correct because it's positive this time. We can use equation 1 to solve for I1, giving us a value of 0.38 amperes, which is also positive, meaning we got the correct direction. Now, if you will report the values of the currents through each resistor, you can drop already the negative sign if you have 1. The negative sign is important when you will solve for the other currents, but for voltage across and power dissipated, we will use positive values. To solve for voltage across each resistor, we use the formula V is equal to IR. So for the voltage across resistor 1, we write 0.38 amperes times 4 ohms. This will be 1.52 volts. Same pattern for the voltage across R2 and R3. So we will get 8.46 volts for R2 and 11.55 for the voltage across R3. And for the power dissipated by each resistor, we can use the formula P is equal to I times V. Therefore, the power dissipated by resistor number 1 would be 0.38 amperes times 1.52 volts, which will give us 0.58 watts. Same idea will be applied to R2 and R3. So the power dissipated by R2 would be 35.79 watts and 44.47 watts will be dissipated by R3. You can use simulations like this one by the University of Colorado to compare your answers. Make sure to use the same values for the resistors and voltages, as well as the connections of the wires and the terminals of the voltage sources. The currents are pretty much almost the same. As well as the voltages. Small discrepancies due to the rounding of numbers. Well, in summary, Kirchhoff's rules are a little bit confusing for some, but you can master Kirchhoff's rules by practicing. So that's it for me today. As always, keep solving.